recording. Okay, so today we're going to concentrate on the ring, star, inline, or chain, and a bus topologies. Let's talk about what topology is. Zoom in a little bit so we could see things better. Network topology is the arrangement of a network, including its nodes and connecting lines. All right. Nodes and connecting lines. Nodes are the devices. What's a device? Well, the device, a computer is a device. A PC, a personal computer. A laptop is a device. A cell phone is a device. Tablet is a device. A security surveillance camera that is connecting, that's communicating with the network, it is a device. Printer, whatnot, all the smart devices. Smart devices, what's a smart device? It's a device that communicates with the network, right? And also they are the active devices. What's an active device? An active device is the one that needs electricity to be powered, either from the outlet in the wall or the power supply that you plug into the wall, or batteries. So a wireless motion sensor for the security alarm, it is an active device because it needs to be powered. Glass break detector for security alarm is an active device because it needs to be powered. It has electronics inside that makes this device work. A door contact would be a passive device because a door contact is just a switch that is operated by a magnet on the proximity. You bring the magnet close to that switch, the switch closes. You take the magnet away from that switch, the switch opens. So usually what happens is that the magnet is on the door actually that opens, right? Because it doesn't require any wiring. Now the switch that is still wired, but it's not an active device, it's a passive device. It doesn't need power to operate. It just provides open and close contact to the circuitry of the security system. So that would be a passive device, right? And the switch itself is mounted on the door frame because it's wired. So you couldn't mount that on the door because you put the wire to the door. How are you going to, there. Now, so again, the arrangement of a network, including its nodes and connecting lines. Connecting lines could be, we distinguish pretty much basic three of those. It's fiber, copper, air. Okay? So fiber and copper will be wiring, will be cables. So will be copper, it's the Ethernet cables that we will talk about in some details in further lectures. So we just call them copper because there will be copper wiring, right? So copper. Fiber, it's optical fiber. We will cover that as well. So these are the cables. Air will be the wireless links, right? So lines, links. Okay, now we distinguish two ways of defining the network geometry. Right? One is the physical topology and the other one is logical or signal topology. So physical topology is how those devices that are part of the network, how they are connected physically with wires or wireless. Now, the logical or signal topology talks about how the signal is routed. And we'll talk about that in the next few slides. All right. Basic elements of a network presentation. On the left side, we have hosts or nodes, and on the right side, we have connecting links. Connecting links, as we talked about, copper, fiber, air. Right? Copper is the electrical wiring. Fiber would be the optical fibers or fiber optics that utilize light pulses instead of electrical signals when it comes to copper wiring. And air would be the wireless. Right? And on the left side, nodes, part of the network. What are those devices? We computers, wireless access points, routers, switches, hubs, bridges, gateways, and all kinds of other things, wonderful things that make noise and flashlights. Printers, other devices such as IP cameras, Internet Protocol cameras. Right? So the cameras security, mostly we're talking about security or surveillance cameras. Few years back, there would be those so-called analog cameras. So the camera would have a wire that supplies the power to it, and it would produce a video signal, and usually be connected to a coaxial cable. And that would provide the signal to the video recorder, DVR, digital video recorder, or VTR. There will be even older ones. There will be those the VCRs. It would be the videotape recorder or time-lapse recorder. But what's a time lapse? Basically, the time lapse would be there would be a more sophisticated version of a VCR, videotape, video cassette recorder, or a VTR, video tape recorder. And the signal from multiple cameras would be multiplexed. What's a multiplexing? It's looking at one camera at any given time and switching between the cameras kind of in a fast way. Right? So it would record a split second from one camera, switch to another camera, switch to another camera, switch to another camera. And if it happens very fast, when you play it back, that machine, that time-lapse recorder, would be able to synchronize with only the signal coming from that camera time recorded during that time. And it would be a little bit like a strobe light kind of a version of the recording. You would see a bit of a jerky move, but you would still be able to see what's happening on that camera. So that would be called time-lapse recorder. Now, these days, and well, the problem with that was that whoever would be taking care of that video surveillance system, they would have to basically keep changing the tapes, the videotapes, every morning or so on. So you could set up that you could have the VTR set up so it loops. It records 12 hours on one tape or 24 hours on one tape. So of course, 24 hours would be less of a quality. Things would be more blurry. 12 hours would be slightly better quality. All right, and then depending on that, you would have to change the tapes either twice a day or once a day. So that would be the disadvantage of that. Now there's the digital video recorders. The digital video recorders record on a hard drive. And the cameras would still be analog, but instead of having a tape, you would have a hard drive as the recording medium in that device. So, excuse me, you would not have to change the tapes. It would just happening by itself, and you would set up the VTR, whether you want this thing have a less quality of a picture and more of a, so you could have go back like maybe 3, 4, 5 days of what has happened, or if you have less quality, but you will have more recording on the, so this recording would be looped every maybe 2 weeks. Right? Now we have something that's called the NVRs, network video recorders, and those are networkable. And those VTR, those digital video recorders, there's DVRs. They also were networkable, but the network setup was a little bit more complicated because times were a little bit few years back. But now there are network video recorders, and the signal that is provided to the cameras is through the Ethernet cable. So you don't need two cables, you need just one cable. One cable provides the power and the signal to the camera. Back and forth, so you can control the camera, you can get the signal, video signal from the camera, and you can provide the power all on one cable. Right? How is it done? Well, there's something that's called PoE, and it's called Power over Ethernet, and so that means that the cable is providing the signal that goes back and forth between camera and the NVR, and also it provides the power to it on some pairs. We'll talk about that a little bit later, right? So there are not just computers that are part of the networks. There could be other devices. All right. First thing, we're going to look at the ring topology. Right? Ring topology, here's the symbol. And what does it say here? Each node or host, we know what these are now, connects to two adjacent nodes in this configuration in a continuous pathway for signals through each node. Data travels from node to node, with each node along the way handling every data packet. Every node acts as a repeater. So if these are computers, if this computer needs to communicate with this one here, it would send the message along. It will be received by this one, and it's going to say, no, it's not for me. I'm going to pass it along. This one, oh, no, it's not for me. I'm going to pass it along. Oh, this is for me. Oh, thank you. You know, my coffee is ready. Yeah, all right. Things like that, right? So this is the type of a ring topology. There's also, we'll talk about the difference between a ring and a token ring. Now, when we talk about networks, we not only talk about the so-called right now traditional networks, where you have an office building and you have a bunch of computers. These computers in the building that you use in the office environment or whatnot, in the industrial environment and in residential, we are not using ring topology for that. But in some industrial applications, when you're talking about PLCs and otherwise controls that have to do with controlling the machines, a lot of them are using the ring topology or chain topology, which basically it's like one straight line. We'll talk about that too. I said it too soon because the ring topology is also being used within the LAN environment, right? But not to connect the computers to the main location. But we'll talk about what it is. Next slide is going to go. So now, when it comes to NIC or network interface card, right? NIC is a network interface card. Here's a single port NIC and here's a double port NIC. Those NICs, these one here, these are the full size mountable on the PCs. However, other devices such as tablets or laptops and whatnot, they also have NICs. They're just a little bit smaller to accommodate the size of the device. But this one is just basically easier to see, right? So here's a single port NIC and here's a double port NIC, and you can see Ethernet ports on that utilize Ethernet connection, which is basically the computer cable that you're using. All right. Now, when it comes to ring topology, which NIC would be used for a ring network? Is it a single port or a double port when you talk about this kind of a topology? Right? Well, the answer, of course, is when you talk about the physical connections, then you would need a double port because each node has two connections. Right? But if you talk about logical geometry, see when we talk about this here, physical topology and the logical or signal topology, you could also use single port, but the device would act like there will be more processing happening on the device. And we'll talk about that further down this slide presentation here. All right, configuration here. Ring configuration. If you have a bunch of computers connected or devices connected in a ring topology, they would be connected like that. Now, when it comes to single ports, the signal would be traveling into this machine, and this machine would repeat and send it back to the main network and repeat. So you could have single ports and still have the ring logical or signal in a ring configuration. Not sure if it's used these days as much as just a regular star topology, but I'm just showing you that that technically it is possible to accomplish the ring logical topology while having something other than physical ring connection. Now, applications for a ring topology. The first slide here shows WAN and MAN, right? Remember, WAN is the wide area network, which would be the internet, and the MAN would be the metropolitan area network. Let's see, this is a part of the city, and these buildings are connected in a ring topology. They can communicate in a ring configuration. Now, over here, you can have them connected in ground through a fiber, or it could be copper, but it's less practical. You know, if there's a physical link connecting two buildings, most likely it's going to be a fiber. Or you could have a wireless connections as well. Right? Now, the difference between a ring and a token ring is that in a ring, the data travels only one way. Only one way. So if this computer or this device wants to communicate with this device, and for some reason this link would be broken, the communication would not happen. Right? But there's a different type of technology that is also used. It's called token ring. Basically, the communication can go both ways. So if this link is broken and the device tried to communicate and there is no answer for the calls, so to speak, then it's going to try the other way to see, maybe it's going to find that way the addressant. Okay, so token ring and a ring. In the ring topology, the data travels only one way. In token ring, data can travel both ways. Okay. Also, a ring topology applications in a LAN configuration. Remember LAN when we talked about the network types, local area network. When you have a LAN configuration, which is utilizing star topology, which we'll talk about the next one here. In star topology, the computers are connected to one central location. And what brings those computers, what makes the communication possible with all the devices is something that is called a switch. Now, switch is capable of only so many ports because it goes one-to-one. This computer has a cable. It's connected with a cable to a jack in the wall. And the computer jack in the wall is connected to another jack that is in the patch panel. That patch panel is connected through a patch cord or patch cable into the single port of a switch. So each individual computer is connected to a physical single port. Well, what happens if you have more devices that the switch is capable of providing? Because the switches can be 6-port, 8-port switches, there could be 12-port switches, there could be 24-port switches, there could be 48-port switches. But what if you have a facility that has like 600 devices? So one switch won't be able to handle the whole thing. So you need to add more switches, and those switches are going to be connected in such way that all these connected switches are going to act like one big switch. So in the LAN configuration, you could connect those switches in something that's called a ring topology, right? So the switches in the main communication room, they will be connected in a ring topology, and each and every individual computer will be connected in something that's called a star topology. Okay? Now, next slide here. I want you to watch these videos when you download this PDF version of this presentation in the student items, like posted lecture notes. Here's a video that's 7 minutes and 21 seconds and talks about the differences between the hub, a switch, and a router. I want you to know what the equipment is, because when it comes to installing or servicing infrastructure, network cabling is all about infrastructure, is the hardware part of it. Sometimes you're going to be asked to install physically a hub or a switch or a router or a modem, then you need to know what they're talking about when they give you the service call. So I want you to know the difference between a switch, hub, and a router, at least. Okay. Now here's another video. Now this video is long, but just play up to 1 minute and 42 seconds. I found that there. Right? This person there shows connecting the switches in the ring topology. And then after that, he talks about setting up a specific kind of equipment as far as the programming it. So we're not going to talk about that. So just these two videos, watch those. So it's going to be what, something 8 or 9 minutes out of your life, right? But you will know what you need to know. Right? Now, talk about star topology. Right? In star topology, here's the symbol for that. You can see one central node and everything is connected to it. Right? So you can say that, you can say that all the wiring from each individual device, those wires home run to central location. Right? So let's just kind of read some of that text here. In the star topology, each node or host of a network is attached to a central node. Okay? Got it? Got it. All right. The central node is usually a hub or a switch. And after you watch those two videos there, you will know what the difference is between hub and a switch. Hubs are not utilized anymore, but you need to know what a hub is and what the difference is between a hub and a switch. And I will ask you on some of the tests what the difference would be. Now, the central node can also be another proprietary device, such as NVR, network video recorder, in surveillance systems. So it could be a switch or it could be other. So the NVR in the security surveillance cameras, the NVR would be the central node that all the wires run to it. Right? All roads lead to Rome. Now, star topology is the most common physical wiring configuration considering the horizontal network wiring. Mouthful here, right? I'll explain to you what horizontal network wiring. Basically, what I'm trying to say here, the star topology, when it comes to traditional, so to speak, network, office environment, industrial environment that would utilize desktop computers that are connected to the central location, wireless access points, they're connected to something. Well, they're connected to the same central location that all the computers are. There could be telephones, VoIP telephones. We'll talk about that as well in further lectures. These are voice over IP. So the telephones, instead of connecting to a telephone switch, that's a separate piece of equipment and it has nothing to do with the network. Now the telephones are capable of connecting to a network, and they work as just like a mini PC, but it's not a PC; it's a telephone. Right? Instead of having a screen and a keyboard, it has a built-in keypad and it has a handset and it acts like a telephone, but it basically, like electronics, communicate the same way the PC would with the network. All right. So so the central node can also be another device, proprietary device. Proprietary is a dedicated, it's a piece of equipment that's dedicated for a specific function. Now, such as video. Okay, so talk about that. Star topology, yeah, the most common physical configuration. When you're installing a network, you are going to be home running every single jack to the central location. When it comes to the regular network, office environment, industrial environment, well, sort of like office, because if there is a computer on the production hall that some supervisor uses, that would be part of the office network. Okay, so those are being installed in a star topology. Every cable from every jack runs to the central location. Where is it terminated? At the patch panel, and the patch panel from that port is connected to a specific port on a switch. If you have 600 devices, including all the computers, all the wireless access points, all the printers, whatever else is connected to the network, if you have 600 of those devices In the central location, the communications room or the computer room, you will need 600 ports. Yeah. Keep going. Star topology. Here is the visualization of what star topology is. Here's a switch, and all the wires come to it. That's the pretty much more the most simplistic way of looking at it. In reality, it looks a little bit different, because could you have a whole bunch of computers in the office, and could you make a cable for every computer? That cable would have a male Ethernet jack on one end and a male Ethernet jack on the other end, and it would just make a hole in the wall, pull that cable out, and plug it straight into the computer. Could you do it? Yes, you could. Or you could have another male jack that would be just running from the ceiling somewhere and plugged in straight into the port. Could you do that? Yes, you could. And you could do this if you have at home network that utilizes maybe 3 or 4 computers. Right? Or sometimes I've seen that happen in small business, such as, like a tire changing shop or, something like that. Yes, you could get away with that, but this is not the way it's being done properly in the industry. In the industry, you terminate that cable onto a jack, that you mount that jack in the wall, and the other side of the cable, you terminate that permanently on another jack that is basically not in the wall, but it's in a frame. And in that frame, you have a bunch of those jacks just to conserve space. And that device is called a patch panel. All right, so you have a permanent installation here, permanent installation there. You could plug things in and out, but that link is not touched. This way, you could run a test. You can test that connection. You can save the test results, and depending on the device you're using for testing, you can actually provide something that's called a certification of Cat5e specifications or Cat6 specific, whatever the category is. And quite often when you're installing some serious networks, the client is going to ask you to install the jacks and certify all the connections. So you do the tests, you save the test on the device, and then give them the file. And it's going the test, each test result collection is going to show you the basically parameters of the cable, how well it performed, and it's also going to tell you the length of the cable as well. All right, so here's the star topology. All right, but this is the simplest way of explaining. In reality, that's what it looks like. All right, all cables home run. This is the rear of the equipment rack over here. Those wires come. Can you imagine? Just this is a lot. Like this is 24 ports here. Right? 24 ports, 24 ports, 24 ports, 24 ports. Can you imagine how many of those connections there are here? Can you imagine just terminating those male jacks and just plugging them in here? It would be a mess. And what if you need to troubleshoot something? It would look like a big spaghetti, right? I like spaghetti, but not wiring spaghetti. Does star topology have to be cables physically connected to one common point, or can it be wirelessly a bunch of devices connected with a Wi-Fi router? Good question. All right. And remember when we talked about the links? So the physical will be the wiring, and then physically that wiring would be connected to one port of the switch, will be connected to a wireless access point that's somewhere in the ceiling, or on the wall, in the hallway. We have a bunch of them in the college. So that would be something like a double star, right? It's still considered a star, because here's the switch that one of the port is connected to wireless access point, and the wireless access point connects to whatever device is in the area, providing it has so many channels available, and that is also a star, but it's kind of invisible star, right? Because you don't see the links, physical links, because you're not running a wire from your cell phone, but you're having that connection. So yes, it is a star. So that also would be considered as a star. Yes. Well, I hope I answered the question. But for the most part, when it comes to installing the cabling for a network, that's what it looks like from the rear. Now, this tells me, when I'm looking at this here, it tells me that this is probably Cat6 cables, because I'm just looking at the thickness of that, and it does look like a Cat6. Cat5e would be slightly thinner, but what's a giveaway here is that Velcro is being used. Now, Velcro also can be used on Cat5e, but if you use zip ties and you don't tie them too tight, you can get away with connecting Cat5 or bundling Cat5e cables. However, some companies that you would work for, they would have strict standards, never use zip ties on any of the data cabling, and that's it. That's the company policy, blah, 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 right? Now, doesn't matter what the company policy is, when you're installing Cat6 cable, you should never use zip ties, because when you use zip ties, they are too narrow and too hard on the cable. And once you squeeze those zip ties, you are slightly deforming the shape of the cable, and that's enough to alter the specifications of the cable, right? So that's why Velcro is being used. And not only Velcro is being used, the soft side in Velcro is being used. So these are a couple of examples of the back of the patch panel. So you see how many cables how many devices are being used here? 24, 20, actually, 24 and 24. So here's 48, 48, 48. See this top and there's a bottom row here, right? So 24 plus 24, that gives you 48, 48, 48, 48. Just get your calculator and add those, how many devices are connected to this particular network, right? It takes a lot. This is not like a few days installation. This installation would take probably a month or two, right? Depending on how many people and what other trades on the construction side are doing. Right? Now, here is the front of the patch panel. So this will be the rear of the patch panel, where the cables are disconnected and terminated, and the front of the patch panel. On the other side of the patch panel, we have ports, and we are using short version of the patch cables, patch cords, to connect the dry connection that comes out of the patch panel, which leads to another jack in the wall, and that another patch cable is being used to connect the computer to it, right? And from this here, it has to be connected somewhere. On one-to-one basis, it's connected to the port of the switches. So this will be the patch panel here. Also, there will be a patch panel here on the bottom, and some of those patch panels are connected straight into the ports of the switches. Each individual jack on the wall has a dedicated port that's physically connected to a switch. Right? So that will be the start topology in LAN configuration. All right, here's a visual on the start topology, just to show a simple way of doing it. Here's a wall plate, has a jack in it. Here's a cable that runs whichever way it runs. It could be in a conduit, up the wall, through the ceiling, in a tray, and then come down from the ceiling in one central location to a patch panel. And in the patch panel, on one-to-one version, it is connected. Every single port is connected to a switch. These are the patch cables. Okay. And notice, remember I've talked about horizontal runs here. This will be a horizontal run. Why is it called horizontal run? Because the wire goes up, so that'll be vertical, right? And then it goes horizontal, and so it's horizontal in the ceiling, and that's coming down in the wall, so it will be vertical. So it wouldn't be like a combination of horizontal and vertical. No, that's not what it's meant by that. What's meant by that is, I'm just going to jump the slide here. Come on. And here's the train. And let me just find the slide that I'm looking for. There it is. All right. Looks like I jumped the slide. Now, horizontal run. Let's say this is a building. All right. Here's the main cross connect, or sometimes it's called main communications room, or sometimes it's referred as electrical room. Or sometimes it's called as the demarcation point. Demarcation is a point of entry. So all the stuff that the internet, all the communication, it will be provided to this, right? This here, the main cross connect, would also be probably in the same room as the first, on the first floor. It will be the same room, but not necessary. Now, this here is considered as a vertical run. Sometimes it's referred to as a riser. In all the commercial buildings, most of them, if they're properly done, and most of them are, the communications closets or the communication rooms or the LAN rooms are pretty much in the same spot as far as floor is concerned, so you could run the cables vertically on it. Right? And it's also considered the backbone or a riser, because it's a riser. So there will be a bunch of holes in the floor and in the ceiling in the next room, next floor, and there'll be a hole in the floor or opening, whatever it is, pipes, sometimes conduits, sometimes just openings, and sometimes just like a shaft, like almost like a miniature elevator shaft that all the wires are going. So this will be the vertical runs. Now here are the horizontal runs, which will be considered in the floor. So yes, the cable sometimes goes up, sometimes goes sideways, and sometimes goes down. Yeah, okay, that's fine. But this is considered a horizontal run. It will be the devices that are connected to the same closet on the same floor. There was a question here. Sorry to interrupt, but my Wi-Fi is super messed up and keeps dropping. This will be posted on the YouTube, correct? You know what? Yeah, I can post that as a version B. Okay. I was just going to post yesterday's lecture, but why not? Let's post both of them. Okay. All right. So that's the idea of a horizontal run. Right? Now, also, what I'm talking about, those horizontal runs could be arranged a little bit different. They don't necessarily have to be from floor to floor. They could be on the same floor, but have different intermediate distribution frames, right? So let's say here's the main distribution frame where everything runs to, and the main frame will be only one, and would have a bunch of intermediate distribution frames, or intermediate, sometimes, well, there are different names. Over here is referred to as intermediate cross connect, or sometimes called a frame or distribution frame, right? Let's say yesterday I gave the example of a Home Depot. I'm going to tell you here too. If you go to a Home Depot, sometimes just look around the walls. Yeah? You're going to see some black boxes about half of a refrigerator size, and they're going to have labels, big labels that is going to say IDF A, IDF B, IDF C, and so on. And they would be dispersed all around the building there. Right? These would be the IDFs. They will be intermediate distribution frames that have a bunch of switches connected in a ring topology. And those switches, whatever the amount of ports they provide, sometimes you need one switch, sometimes you need 5 switches in that closet, right? On that frame. The idea is that those are dispersed strategically around the area, so the longest run from that frame of a cable end to end can't be longer than 300 feet. And we will also later on talk about the specifications of the cable. Right? So that's why there's not only one distribution frame, and then you can have longer cables going to each computer. No, those IDFs are placed so the longest cable cannot be longer than 300 feet. As far as copper, or we're talking Cat5e or even Cat6, but mostly you're going to see Cat5e over there. Right? And then all those intermediate distribution frames are connected, they home run in a star, so it's a double star. Each IDF has a star topology that connects all the computers that are connected to it. Computers, cash register is a computer as well. And then those frames again are connected in a star topology to the main distribution frame. So it's got double star, right? Star that disperses into another star. Right? You can go on and on, right? So the reason for that is that those IDFs are connected to the computers with the copper cabling, no longer than 300 feet. Those IDFs are connected to the main distribution frame, which would be the MDF, and there's only one MDF because it's main distribution frame, right? And there could be many IDFs. Right? So that one is connected. Those IDFs are connected to the MDF through the fiber optic lines, because they can carry the signal over longer distances, right? Longer than 300 feet, maybe at 2 or 3 kilometers, right? So the slack is there, right? The headroom is there, all right? So that's the idea. So yeah, so but I just need you to kind of absorb the terminology. Horizontal runs are the ones that are connected to one distribution frame. What are the videos we need to watch on YouTube called? Yeah. When you go to our classroom portal, here is what is our classroom portal. And in the announcements, I always leave that one there. I will never erase that one. Go down. Oh, look, here's our YouTube playlist. All right, click on that. It's going to take you there. That's our YouTube playlist. First part of it is going to be all the lectures. And after the last lecture, so here's yesterday's lecture, network topology. And I'm going to have a lecture, another one, network topology repeat or something like that. So going to be another one today. And after the last one that we did, the lecture is going to be the lab instructional videos. So that's where you find those videos. Yeah? Okay, so now let's keep going. We already seen this one here. Now, bus topology. No problem. Yeah, so if you need to go to another, because we're taking a bit longer time doing this. If you need to go, by all means go, and when I post that, you'll be able to see the ending of that. Or if you want to stay, you're welcome to stay here. So here is, and I'm just going to continue, and I'm going to post that so you can watch the ending. Bus topology. A bus is the main transfer line. Right? And somebody asked me if it was an acronym. No, it's not an acronym. It's a meaning of a main transfer line. It's just like a main river, and everybody taps into it. The bus topology was used in LAN setting until early 1990s. So the computers will be connected to one bus line, will be a coaxial cable with the tap-in connectors, and the computers would be connected. It would be much slower than the technology was a little bit different. But that's what we used to do to connect the computers. Presently, and this is not 2019, it's 2022, all the horizontal systems are wired with a star configuration. Does it mean that the bus topology is out? No, it doesn't mean that the bus topology is out. It's still being used. in various different scenarios. Like for example, in the logic controls, the controls that that are controlling the machines. So there would be an industrial machine that would need like would have a control module connected to it that communicates with the whatever else, and those quite often are connected in a bus topology, right? Or sometimes they're connected in a chain topology, right? Depending on the manufacturer of the controls. Actually, they're more in a chain topology than the bus, right? But here is another example of a bus topology. Here is an alarm system, fire alarm system, and a security alarm system. Let's take a look at the fire alarm system. Fire alarm systems and security alarm systems have something that's called zones. A zone is a individual circuit that senses a condition presented to that circuit. That circuit can have one device connected to it, or that circuit can have multiple devices connected to it. Like for example, if it's a zone that is going to have couple of or two or three or five smoke detectors in one room, then all those smoke detectors in one room can be connected onto one circuit, because if there is a smoke detected in that room, you don't need to know that there's a smoke detector number 3 that senses that. Most of them all pretty much what is interesting is that there's a smoke in that room, right? So you can just save up the zones, right? Because you can only have so many zones in whatever the device is, the system, right? The panel. So here is the fire alarm example. A fire alarm zone, which basically is a loop that senses the condition. And then with the fire alarms, you can, most of the time, you're going to have sensors that sense either smoke or heat. Also, there are other triggering devices like pull stations or automatic kitchen stations. That's a little bit different, kitchen systems. So let's talk about zone. A zone in a fire alarm is a loop that is connected to a end-of-line resistor, and it's connected back to itself. All the devices that are connected to it are in the open condition at rest. So that zone doesn't even see those when nothing is happening, because these are normally open. But it sees the end-of-line resistor. Why do we have the end-of-line resistor? To make sure that there is nothing wrong with the main bus. Because if that line somehow gets broken somewhere here, then if we didn't have that assurance in terms of end-of-line resistor, we wouldn't know that this line is broken. So if that is broken somewhere here or anywhere, the system will not see that resistance that it's looking for, and it's going to kick into something that's called a trouble condition. Doesn't mean it's a fire condition. It's just a trouble condition. That means there is something wrong with the sensing line. And when it's in a trouble condition, it's going to produce annoying beeps. So whoever is in the area there, they're going to be annoyed by those annoying beeps. And they're going to come over, where was those beeps coming from? Oh, it's the fire alarm panel. It says trouble, call this number for service, or so on, whatever, right? So then the service company is going to come over and figure out what's wrong, right? Now, when there's a condition, let's say there are a couple of heat detectors and there's a couple of smoke detectors. If one of them triggers, then it's going to close the switch. So that means it's going to short it out. So the resistance is going to be the resistance at this zone here. It's not going to be the resistance of the end of line. It's going to be a dead short. Then this zone is going to trigger into a fire alarm, right? And it's going to say fire hallway number 2 or whatever, right? So here is the example of a bus. All right. Now here's another example of a bus, and now there's more complicated. It will be like a data bus. Here is the magnification of a security alarm panel. The ones at the left here, there's a plus and minus, and it says auxiliary. Right? So that's providing a 12-volt power to the active devices. Right? The active devices are the ones that need power. And there are zones. Here's a common, and zone 1, zone 2, and so on. So if you have a loop that says motion sensors in room somewhere, bedroom there, or cafeteria or something, they will be all connected, could be connected to that one zone. But also, here's the bus, right? And this is green and yellow. So usually the cable that is connected is called a Z or Z4 cable, which is the old color code configuration. It has red and black wire, and it has yellow and green, so four conductors. So in a security system, the black and red are being used for power if it needs. So yes, this keypad here would have 4 wires connected, the red and black for power and the yellow and green for data, but I just didn't put those power in there just so to kind of have things more clear as far as the picture. But look at this here. That yellow and the green line is one data bus. It's in the bus configuration because those 2 keypads, they're just tapping in to the same pair. So it's a bus configuration, and this thing can go on. You could have more than 2 keypads, 5 or 6 or 7 keypads, depending on the facility, and each individual keypad will be able to use that data line simultaneously to communicate with the main panel. So it's a bus configuration, right? Inline or chain topology, right? Okay, so here's the ring topology we talked about, and this will be a chain topology or inline. If those switches in the LAN room were connected in a ring topology, this would be it right here. If they were connected in an inline or chain topology, they would be connected in this way. We're going to skip the idea that why would you want to choose one over the other. It just sometimes they're connected this way, sometimes things are connected the other way, just to visualize, just to show you different types of connections. Of course, the ring topology will be more efficient because if the link is broken here, the switches still can communicate. And if this link is broken here, yeah. But this is the difference between a ring and a chain configuration. And the chain will be the symbol for that. All right. Now I'm just going to give you a couple of examples here from the real world using the real piece of equipment. This is the simplest one. Here's a switch and here's a switch. Here's a PC, here's a PC, printer and printer. Over here, these 2 devices, the PC and the printer, they're connected in a star topology within this network. Advantage of that would be multiple users can print. It will be an office environment having a huge expensive printer, and whoever the office workers, they can use that printer whenever they need to print. If somebody wants to have a personal printer in their office, they can connect that inline. So this printer is connected inline, or the PC is connected inline with the printer and the switch here. So this will be inline configuration. Here, another example. And I'm just going to throw the technical lingo as far as devices that are being used in the real world. Of course, we have inline topology here. What is this here? It's an Ethernet extender, right? As I talked about, and we'll talk about a little bit further, when it comes to copper connection, which would be the Ethernet wiring, you can have no longer than 300 feet. Or 100 meters. It's actually 328 feet. However, you don't want to install end-to-end from the jack in the wall to the patch panel, end-to-end the whole wire, longer than 300 feet. Because from there, from the jack wall from the jack, from the wall jack, you also have a patch cord that connects to the computer. It is going to have few feet, right? And then the patch cord also is going to have certain length, right? So 300 feet is the longer distances. If it's longer, then you might lose some of the data. The data is going to trip over its own feet, and so to speak. Normally, you're going to say that the data might lose some packets, right? So the data might be incomplete, and you're going to have incomplete communication. So it's going to work sometimes, and sometimes it's going to, okay, there's a glitch or something like that. Right? That's probably because, well, the having the cable longer than it's supposed to be, 300 feet, that would cause that, definitely, right? So what if you can't fix the distance, right? I mean, device is where it is. Are you going to build another communication closet and use the fiber? No, you don't necessarily. If the speed is not the object, let's say you have some intensive video communications and so on, then yeah, you would need the speed for that. But if it's a cash register that just basically makes momentary connection with the mainframe, and it just sends a couple of numbers. It doesn't matter if they're 1 millisecond or 1, microsecond. The numbers are going to get there, right? Because somebody bought a chewing gum somewhere, right? So you could use something that's called a Ethernet extender, and that Ethernet extender is connected in line with the whole link. Where does the Ethernet extender? Because the Ethernet extender is a smart device. It's an active device. There are two ways of powering it up. One way would be the power transformer connecting to the wall, but sometimes you don't have that possibility because it's somewhere, wherever the link is, right? You can use something that's called a PoE, power over Ethernet. And the power over Ethernet is that those ports on the switch, they are also capable of providing power on some pairs. So when you connect that one link through that cable, this device gets its power from that cable and it gets the signal. Some switches are capable of having a PoE, and some switches, were less expensive, are providing just a signal. So we need to make sure that if you want to use PoE, you gotta make sure that the PoE is available. PoE is available on that switch. So when you apply the Ethernet extender, then the data is going to be traveling not as fast. You won't have that full speed capacity of that specific Ethernet category cable, but you can still have proper communication without data being lost with the transmission. Ethernet extender. Wireless access point. Okay, here's another device. It's called a Poe injector. If you have a switch that is part of the already working network, that it doesn't have the PoE capability, you can, if you have one device that needs PoE, this will be the wireless access point, you can connect the power, but what if it's in the ceiling and there is no outlet in the ceiling there, right? So you gotta use PoE, but well, okay, this switch doesn't have PoE. What do we do with it? Well, there are devices that are called PoE injectors. If you just need one, instead of replacing the whole switch and reprogramming and the whole shebang that goes with it, you can just buy that device. And of course, that's going to be at the equipment rack location. So there's going to be a bunch of outlets here, the hydro outlets. You can plug that in to power it up. And one patch cord is going to go into the port of the switch to get the signal out of it. And the whole thing is going to inject the PoE on the other port, and the other port is going to be plugged in. It's going to be used to plug in the wireless access point, which needs power and the signal. So PoE injector is connected in line with the wireless access point. The last device here is the VoIP telephone system, voice over IP. VoIP telephone systems are pretty much the thing to go right now. That's the way to go. A lot of companies are switching from the traditional telephone systems into the VoIP telephone systems, and we will talk about that. But the companies who produce the VoIP systems, they want those things to be purchased. And because they want them to be purchased, they're going to make it as easy as possible for them to be installed, which means because they need a Ethernet port, which would be the computer port. Well, what if that office only has one and the computer is connected to it? Well, they thought about that. They can put that phone in line with the PC that's on somebody's desk. So you can plug in the telephone into the data jack that the PC used to be plugged in. And then from there, there's another port you can plug into the PC. And the phone is going to get its signal through the logistics of things, and it's going to sense its own signal through the same cable. And the PC is also going to sense its own signal, and the whole system is going to work as it was. Very popular in the department stores. If you look at some of the big department stores, the POS stations, point of sale stations, or otherwise, there will be a computer and there will be a phone, and there'll be only one data jack. So that's how things are being connected. We'll talk about the VoIP systems in greater detail further down the road as we go along. Now, that's the last concept I'm going to share with you here. Here's a switch, right? And here are the devices. Are the PCs connected? Remember we talk about the physical topology and the signal logic, signal topology, signal routing topology. So that's the another version of explanation that I'm going to give you here. So are these PCs connected to the switch in a ring configuration, or is it a star? Physically look like it's a star configuration, and it is. Can the system work as a ring? And I think we actually talked about that in the first few slides. Yes, it can work as a ring depending on how this device is configured. I don't see why it would make things work as a ring, but if somebody really wants to, really being stubborn, yes, they can configure that or make a device. Don't know why they would, but depending on how this switch is configured, it could work as a star, and it could work as a ring topology, which means logically the signal would travel from one computer to the other instead of just communicating with that. I don't see the use of that, but I'm just trying to explain to you the difference between the physical and the logic signal. Lab foundation. All right, last couple of slides. This is what the patch panel looks like. This is what a jack looks like. All right, a patch panel is basically a bunch of jacks, data jacks, arranged in a kind of array on the one frame to conserve space. Those jacks, when you mount them on the wall in the wall plate, yes, they look like this, and they have the connection ports right here. If you need to connect the other side of the cable to another jack, you're not going to have a bunch of wall plates on the other side, because you would just run out of space if it's like a 600 computers type of an office, right, or a building. To conserve the space, you arrange those jacks in a patch panel configuration. So here's the port, and here's the connection terminals, and here's the port, and on the other side, here's the connection terminals that correspond to each and every jack. All right, a couple of cables. One is Cat5e, and here's Cat6. Doesn't mean, because this one is in green, this one is in blue. They come in different colors, doesn't matter what category. All right, so you can get in different colors, usually blue or white, green, whatever. Now, if you look at this thing here, they have a twisted pair configuration. They are twisted pairs. The pairs have a twist to avoid the crosstalk or the interference from one pair to another. So in Cat5e, which is the earlier standard, and E stands for extended, you can see pairs are being twisted in a different way. The reason for that is that if you have two cables, or if you have cables that are straight, they could interfere with each other, because creating an electromagnetic field, and that field would induce the signal onto another, and you could have a mess as far as signal being bleeding from one pair to another. If you make a twist, the electromagnetic field is not as steady along this pair, and if you have those pairs twisted in a different rate, then there's even more difficulty for the signal to jump from one pair to another by the induction. Right? So that's Cat5e, twisted pair. Now Cat6, it does have twisted pair, but you can see the twists are a little bit more solid, and we'll talk about that too. But it also has a separator. So the pairs are not only twisted around themselves, the plastic separator is just like a, looks like this, right? And it has a channel for every pair. So the pairs are not only twisted around themselves, but they're also twisted as they go along, because that separator twists as it goes along. So they are also twisted around each other. So it's just to basically make the crosstalk or interference between pairs more difficult. All right. And here's the last slide. The connections that we're using, it's called an IDC connection. That's the punch down. IDC stands for insulation displacement. Here's the IDC connector. It has a spare here, right? Like a slit. You have a conductor that's basically insulated. Here's the insulation or isolation, dielectric, because you don't want them to conduct electricity between each other, right? So they're isolated. If you lay the cable, the conductor here, and you force it into this connection, that connector is narrow enough that it's going to bite into the insulation and it's going to make a contact with the conductor inside. So that's why it's called isolation displacement connection, IDC. Most of the data connections and no telephone connections that they're using this type of connection because they are fast to do and they're quite reliable. The one thing I'm going to point here, I got this picture from the internet and it shows a stranded cable. No, no, no. The isolation displacement connection is designed for a solid core conductor, right? So this is wrong here. I got this from the internet, but I left it like that. I could Photoshop it and make it solid, but I said, you know what? I'm just going to explain that because sometimes you're going to run into a stranded cable or conductor and somebody's going to ask you to make an IDC connection and you can just point it out. No, it's not designed for that, all right? Simply because if you have strands, if you punch it down, and that thing bites into the insulation, it can bite into some of the strands of the conductor and break them away, right? So that's not a very reliable situation when it comes to stranded cable. And over here you can read a little bit of a history or whatnot. This is basically what the insulation, where am I? This is the IDC in action, just an example of a data jack or a phone jack, but mostly it will be data jack, that you would have those IDC connectors here. They look like this, and I'll have, if you watch those videos, the lab instructions, you're going to see that. These are those connections here, and for this one, we will be using a punch down tool to force those in. And the punch down tool does two things. It forces that conductor into the connector and it cuts off the remaining part of the conductor. All right, so that's pretty much it for the for this class. This is the last slide. We have one person left. Everybody else is gonna see that the ending of it on YouTube. All right. Wyatt, thank you for sticking around, and I will see some of you guys in the lab section 1A today. Okay, cool. Thank you, and have a good day.